Radio check. This is Roche Orbital, broadcasting from deep space. We are currently orbiting a neutron star. It is releasing alarming amounts of energy, so comms have been struggling to get out. Since we're here, I figured today we should talk about them and their insane physics. The life cycle of a star is a fascinating topic that has many stages. A neutron star is not the beginning of a star, but the death of one. This neutron star was once a very massive main sequence star that was turning hydrogen into helium with nuclear fusion. Gravity is always pulling the star's mass inward. This causes the core to heat up to unimaginable temperatures. This superheated core then fuses atoms to make new elements. This fusion of atoms releases energy outwards, which allows the star to stabilize. The bigger a star is, the more energy is required to stabilize itself, which leads to the largest stars having the shortest life. As the star runs out of hydrogen to convert to helium, it begins to make heavier elements, like magnesium and oxygen. This intensifies the fuel being used, which then leads to silicon and iron being created. At this point, the star is close to death as gravity starts to overpower the energy from fusion. A cascade effect occurs very rapidly as the star can no longer support its own weight, and a supernova explosion is triggered. This explosion throws the star's outer layers into space in all directions. All that is left is the core, which becomes a neutron star or a black hole. If a star is 20 times the mass of our sun, it will turn into a black hole at the end of its life. If it is between 8 and 20 times the mass of our sun, then it will become a neutron star. They're called neutron stars because as the original outer layers are stripped off in death. Sorry about that. Lost comms for a second. Where was I? Okay. So after death, the remnants are made of mainly just neutrons. On the thin top layer are very heavy atoms like iron. Below this, electrons are pushed into protons to make a neutron soup. And even deeper, in the center, protons glide against electrons to make a very intense magnetic field around the star. The gravity from a neutron star is very intense, and I'm going to do my best to explain it. Imagine a fabric stretched across a small plastic pool. With tension on all sides, it becomes a flat plane. This is our space-time representation. Now put a basketball in the center. The fabric will dip towards the basketball, and if you let a marble roll down the edge, it will start to rotate around the center. Let's say the basketball is our sun, and the marble is your bunk spaceship. Now remove the basketball and press your fist into the center of the fabric, applying as much force down as you can. The fabric will develop a very steep angle downwards, and that marble might make a few passes, but after a certain point it will go straight down to your hand. In this little thought experiment, your fist represents a neutron star in space-time. They tend to be over 1.5 times the mass of our sun, but crunched down with an average diameter of only 12 miles. This large amount of mass in such a small area creates a powerful gravity well. Our sun's gravity is about 30 times that of Earth, and by some insane physics, the average gravity of a neutron star tends to be 200 billion times that of Earth. Luckily, Roche Orbital has a Geller field on it, so we are not affected by this neutron star's temper. But if you were on a 21st century spacecraft, you would have some serious problems arise as the neutron star's magnetic field repurposed your ship's frame, and its gravity pulled you into a Kelvinized death. That's not a word, but it sounded edgy, so we're gonna keep it pushing. There are different categories of neutron stars, differentiated by certain phenomena that is observed by astronomers. Pulsars are the most common type found, with the University of Cambridge stating in 2023 that over 3,000 had been discovered. They are a relatively new discovery, with the first pulsar being documented in 1974 by Anthony Hewish, for which he won the Nobel Peace Prize. A pulsar's rotation can vary from 4 rotations per second to up to 1,000. This rotation, combined with a strong magnetic field, releases energy in the form of bright jets that shoot out from the star's poles. These jets spray out electromagnetic radiation into space, and as the pulsar rotates, the jets appear to pulsate. This can be seen by astronomers on Earth through radio telescopes. They may be cool to look at, but they also serve a purpose to astronomers, who use them as cosmic clocks to study gravitational waves left over from the Big Bang. Now, what happens when you discover a neutron star with a magnetic field that is a quadrillion times stronger than Earth's? Well, you found a magnetar. A magnetar's magnetic field is thought to be caused by a certain events during the supernova explosion. The star must be very massive and rotating very quickly as it dies. It is also possible that the magnetars are created when two neutron stars collide, as this will increase the total mass of the leftover star. There is a constant battle going on inside of a magnetar. Strong magnetic forces will be attempting to rip magnetic matter apart, but the intense gravity present will keep everything together. Occasionally, cracks form on the surface of a magnetar. The top crust is a thin layer of iron atoms. These fissures form when the poles shift ever so slightly. This leads to an enormous amount of energy exploding out of the star. Astronomers call these starquakes, and this energy released can be seen as gamma rays. Black holes are often described as cosmic devourers because their gravity is so intense that it can pull matter off of a star that gets too close. Well, neutron stars are no exception to this, as accretion-powered neutron stars have been discovered. If a neutron star is in a binary system with a main sequence star, and that star is inside the neutron star's gravity, then the neutron star will begin to consume the other star regardless of its relative size. The main sequence star is always releasing matter. This matter will be absorbed by the neutron star and form an accretion disk. As the matter flows into the neutron star, it speeds up and gains an enormous amount of energy, which releases X-rays. The poles of a neutron star are the entry points. This creates superheated X-ray flashes that can be observed as the neutron star rotates. For millions of years, a main sequence star will be slowly devoured by a companion neutron star. This creates one of the most horrifying yet beautiful dances that can be seen in our cosmos. Well, that's going to be the end of our broadcast. Wait, I'm forgetting something important here. Oh, I remember now. Neutron stars can also power nebulas. Yeah, I'm going to activate Roche Orbital's FSD and get some live footage of one so you guys can see it firsthand. Okay, the station is now a few million kilometers from the Crab Nebula. Gazing upon this cosmic art piece is truly astonishing. In 1054 AD, Japanese and Chinese astronomers noticed an anomaly in the sky. A star so bright it was visible during the day. This new star was in fact a supernova explosion. This star exploded in a beautiful fireworks display, and the light from this took roughly 6,500 years to reach those astronomers' eyes that day. The neutron star that remains lurks in the center of the nebula. The Crab Nebula is considered a pulsar wind nebula, which means when the neutron star was formed, it was rotating very quickly. Its rotation formed a wind of charged particles that merged with the supernova remnants. This fast rotating and highly magnetized neutron star developed an electric field that strips particles from the surface of the star and accelerates them to near the speed of light. This cycle involves these particles releasing gamma rays as they flow with a strong magnetic field. The photons produced begin to decay in electron-positron pairs as they drift from the magnetic field. These new pairs then shoot more gamma rays, which repeats this process over and over again, releasing a lot of energy. This process encompasses the magnetosphere of the neutron star in plasma. Solutions have been found where the plasma collects at the magnetic poles of the star. But if the entire magnetosphere is populated by plasma, the magnetic field is strong enough for the plasma to match the rotation of the pulsar. At a point close to the light cylinder, the plasma changes speed and some particles escape into the surrounding medium. The particles that escape carry away magnetic flux in the form of magnetized wind. Magnetic stresses from the pulsar play a huge role in the shaping of the nebula. The Crab Nebula is elliptical in overall shape, with its longest ends correlating with the pulsar's spin axis. This implies an interconnected relationship between the pulsar and the evolution of the nebula itself. A pulsar is an oblique rotator, which means its magnetic rotation and body rotation axes are not aligned. These counter rotations excite the electromagnetic field, which causes electromagnetic waves. Wind plasma flows throughout the nebula and releases non-thermal electromagnetic emissions that we can observe. Fast-moving anomalies have been documented where the wind starts to slow down, which confirms at this point energy is injected into the nebula by the pulsar. These particles release electromagnetic radiation during the synchrotron emission. Synchrotron emission is when the fast-moving particles are forced to change direction on a dime after interacting with a magnetic field. The synchrotron lifetime of the radio-emitting electrons is much longer than the age of the nebula, so they fill the entire nebula with their light. The lifetime of the optically emitting electrons is shorter than the life of the nebula, so the optical image is smaller than the radio one. Electrons that emit X-rays lose their energy very quickly, so X-rays only exist close to the pulsar. By studying these X-rays, we can see how the pulsar winds affect the nebula's cold gas, while radio and optical images reveal the large scale of the nebula itself. The X-rays track the plasma that is being injected back into the pulsar, which gives us hints at what's going on in this mysterious process. The Crab Nebula's magnetic field and life force can be traced right to the pulsar in its center. More knowledge needs to be drawn from this strange cosmic dance, but in time, with perseverance and curiosity, the answers may reveal themselves. All of us on Roche Orbital, thank you for listening today. I hope you learned something. Seeing your life as an integral part of the universe is called a cosmic perspective. To grasp how small you are in comparison to the scale of the universe is important. Although we may be small, we are all connected to one another, and we are all connected to the cosmos around us. Maybe, just maybe, one day, we will stop seeing other people as them and see everybody as one. This is Roche Orbital, signing out.